this audience. I'm always very thankful to give this kind of community talks. So, what is happening there?
The community is violent.
Wow.
That's called alpha.
So let's perhaps wait for a second until this gets back. So I'm especially thankful for Tom's talk because it already primed you a little bit for what I will talk about. During the last couple of talks, we heard a lot about the bold response, and especially people were interested in the amount of activation. So very often we heard about signal statistics that are analyzing the height of the signal, essentially. I will be focusing on the temporal domain, which already came a little bit up in Tom's talk. So I will tell you that you perhaps can get more from your functional MRI experiments by analyzing the signal in the temporal domain as well. So let me briefly get back to the time course of the hemodynamic response. You've seen this in a lot of publication. I'll skip through that quickly. So the hemodynamic response to a given stimulus has a typical three-phase structure. We see an initial dip, and we then see a large overshoot and some time of an undershoot of a signal. And this is pretty much the same whether we measure the signal with FMRI, what's the bold signal, or with optical methods such as near-infrared spectroscopy. And what happens essentially in these three phases, we already heard a little bit about it. So the initial dip is thought to be a result of a local oxygen consumption. So you have some stimulus, and those neurons consume oxygen, and you have a local reduction of the deoxygenated hemoglobin, or the increase in the deoxygenated hemoglobin and a decrease in the oxygenated hemoglobin. Well, perhaps I should fix this here. The overshoot phase is then thought to be a result of a regional inflow of oxygenated blood leading to an HOB increase and an HBR decrease. And the terminal undershoot is relatively, well, that's not good. The terminal undershoot is largely a result of a change in cerebral blood flow. And we can observe the changes in these oxygenation levels, for instance, using let me check this first. Yeah. I'm sorry for that. Let's start. Great, this way. Okay. So again, the hemodynamic response has three phases: an initial dip, an overshoot, and a long undershoot. And how this comes up is that, first of all, we have a neuronal population that is active, consumes oxygen. So we have a decrease in deoxygenated oxygenated hemoglobin and an increase in deoxygenated hemoglobin. And then we have an inflow of fresh blood into that area, which overcompensates that decrease. And then we have a terminal undershoot, which is most likely a result of changes in cerebral blood flow. And we can observe this effect either with in the near-infrared spectrum, because oxygenated blood simply has a different color than deoxygenated blood. Everybody knows this. Or as a change of magnetic susceptibility, which is essentially using in the bold effect. There are slight differences between those two techniques in which, with respect to the phases that we can see. While we very easily can observe the initial dip in infrared spectroscopy as the intrinsic optical signal, we don't really see it in MRI. and vice versa, the undershoot phase is not easily detectable in the intrinsic optical signal, versus it's very well documented for the fMRI signal. Let me show you results from a little experiment. I got the data from Ron Frostig here at UCI. It's an animal experiment in intrinsic optical imaging. So we have the exposed cortex of a rat, the barrel cortex especially, of a rat over here, and the stimulation is basically whisker stimulation. And this is nothing but an average over 32 trials. So it's a stimulation for about 1 second, and then I think the intertrial interval was about 12 to 14 seconds or something like that. So what we see is that relative immediately after stimulation onset, we see that this negative dip develops and then peaks around at 1.9 seconds after stimulation onset, and then this effect swings over into the overshoot phase, which we see here at 4.5 seconds. That is essentially the end of the recording period. It goes on and still gets stronger. What I would like to draw your attention to is that this negative dip develops immediately with stimulation onset. So while the stimulation is still on, we see this negative dip over here. And you also can see that the shape of the area where we see this negative dip is different from the shape of the area where we see the overshoot, where we see the bold effect. So this means this is thought to be more correlated with the real area of cortical activation, whereas this is somehow related, well, to a vicinity of the blood vessels. And as you can see down here, we have a blood vessel down here, and this seems to be a little bit stretched along the blood vessels over here. And you can do a lot of statistics on this, look at more regions, look at more trials, and Ron has done this in a paper published in 2007 and essentially verify this. This is just an example over here. So we heard a little bit about modeling of the hemodynamic response. In the very essence, we always think there is a neuronal stimulus, and what we measure as the bold response is the result of some process that is very often described as a convolution process. So some stimulus elicits some kind of neuronal response, and that leads to differences in the cerebral blood volume and in the local oxygenation levels, and that all together somehow gives us the bold response that we measure. And a lot of the issues in data analysis that we are dealing with is just the question, how much can we infer from the observed signal about the stimulus, and or about the neuronal response to the stimulus? And this was, for instance, what Thomas was talking about. And there are a lot of complicated models to explain how we get from here to there. For instance, DCM incorporates such a model, and you need a lot of different variables. Some of the variables you already explained in the previous talk that form the shape of this response. But we can be very pragmatical and just take the result and try to model it. And this is the very essence of my talk. I will describe methods for modeling the time curve of the hemodynamic response. So a very simple functional model that you can use here for the negative dip as my first example is a Gaussian function. And I'll later get to some why we're choosing the Gaussian function over here. Suffice to say for this moment that I just want to explain the parameters to you. So we have something like the gain or the height of the response is the beta 0 over here. We have the beta 1, which is the dispersion, sort of the width of the duration proportionate to the duration of the phase. We have the lag, which is the time to the mean, time to the maximum of the response. And of course, we have some baseline term that I do not want to interpret here. The advantage of using this function is that it's an empirical model, but we get parameters that are very easy to understand. They are very easy to understand in terms of physiologic measures, how they are related to my experiment, and this is what I wanted to show to you. So for instance, if we take the negative dip, and this is just a small region around the center of the blue area that we saw before, and this is the time course here in time steps. There were measurements taken every 100 milliseconds. And so this is the pre-stimulus phase, and this is the phase of the stimulus. And you can see when I'm modeling this signal here, which you can see under here, by a Gaussian function, it fits pretty well the negative dip over here. And what you can also see very much is that immediately when he's beginning the viscous stimulation, this negative dip develops over here until the overshoot phase catches in and takes over. And you can also, what we can also do is sort of transfer this into space again by looking at which areas are involved on the onset of this curve and on the outset of this curve, so at the beginning and at the end. And I've simply taken out the time point from the maximum over here, -2 standard deviations, +2 standard deviations, in order to map that. And this looks a bit like art, but I will explain this to you. Remember, this is similar to the picture you've seen before. This is the same view as we had over here. So it's the same area that we see over here. This is our negative dip. And if we go now over here, you see at a time point 0.3 seconds after this stimulation onset. So while the stimulation is on, what we see over here is how much deoxygenation we have in certain areas. And what you can see over here, according to this color scale, is that the deoxygenation develops in areas which are sort of apart from the vessel underneath. So these are areas where oxygen needs to diffuse into. And on the outset, we see that these areas also recover from the vessel, so they get fresh blood inflow from the vessel. And these areas which are a little bit remote from the vessel, of course the oxygen has to diffuse into, so they will recover a little bit later than the other areas that are essentially more close to a vessel. So this is all to say that the boat response is rather a quite stable physiological effect that we have, and it can be precisely modeled, at least on these animal data. So now let's turn over to humans, and let's turn over to modeling hemodynamic responses in functional MRI. As I was saying before, we hardly can have any experiments where we see a compelling negative dip, initial negative dip. So most people actually are interested in the overshoot phase, what is closer way to call the Bowl effect. And the advantage of modeling here is that beside the activation amount, which is expressed as the gain, we get the time to maximum, which we call the lag, and the duration of the response, which we call the dispersion over here. The prerequisites in order to be able to model the hemodynamic response like this is, first of all, you need to have an event-related experimental design. So, of course, with block designs, this doesn't make a sense because all the hemodynamic responses overlap and you won't be able to analyze a single response. So you need to have an event-related experimental design. You need a relatively long interstimulus interval. This is just for the simple reason that they should, you want to model a time curve and they should be separated. And this is why you want to prefer to have an interstimulus interval of at least 8, better 14 seconds. I relax that later, but these would be an ideal case. You may want to have a relatively short TI time, so a relatively fast measurement, because you want to capture the time course at multiple time points. And you need to do a conventional statistical analysis first in individuals, and I get later to this in a second why you need to do this. So what you want to do is then you do the following processing steps. You export the time series signal averaged over an activated cluster. So you have your individual activation maps. You just select a cluster of voxels, average the time series over that cluster of voxels, and export that. And then you can adapt a functional model to each hemodynamic response in your series using that model, for instance. And then you have the model parameters, gain, lag, and dispersion, for each trial in your experiment, and you can combine this with your stimulation conditions. So you can say whether it was a red condition or a blue condition or a phase condition and how long it lasted, and so on and so on. And then you have a table for each region of interest and for each trial. And you can have this times the number of regions of interest you have in a subject and times the number of subjects you have in a group. Could be a large table, but it's much, much smaller than the imaging data you had first. And then you can analyze the influence on the stimulation conditions on the shape of the hemodynamic response by any suitable statistics you can think of. So let us take an example FMRI experiment. This is a very old experiment, but it's a prototypical one, and it's easy to explain. So it's an experiment in language understanding. Sentences in active and passive voice were already presented. They needed about 2.4 to 4.2 seconds for a presentation. And subjects were asked to judge the sentence grammatically on correctness and to respond via button press. So you had active sentences, passive sentences, correct and incorrect sentences, 4 conditions. We did a standard FMRI protocol, taking just 4 slices because we wanted to have high temporal resolution and a relatively high spatial resolution. In this case, we used a trial length of 24 seconds, which is not essentially necessary. But during this, we had about 6 seconds presentation time and an 18 seconds pause. And we had 76 trials recorded in about 35 minutes. Today, you would take much, much more data and much, much more trials in here. Just to show you some results, so we have 2 regions of interest here, one taken from a primary auditory cortex and one from a region a little bit more anteriorly on the temporal lobe. And this is the time series signal that you can see over here. The dots correspond to the exported signal, and the lines correspond to the adapted function. And it's a little bit hard to see. You have a dotted line underneath, which is the stimulation. So it looks like it matches the data pretty well. And now we take a look at the data itself. So this is what you get out of this. These are several regions of interest in an individual data set. And these are just statistics of the gain, lag, and dispersion values. And first of all, what you can see is that you have a huge variation. This is given for a single subject over here. You have a huge variation in gain. You have a huge variation in the time to maximum. And you have a huge variation in the width of the hemodynamic response. All of this is no wonder, because the stimulation conditions changed for each trial. So we have to analyze this information further with respect, for instance, to the sentence length and the correctness manipulation and these issues. But what we can already do is we can introduce a temporal ordering based on the lag values. So we can find out whether this is always earlier than that one, for instance. And this is just a simple statistics. And using these simple statistics, you can introduce a temporal ordering, a sequence by which these regions come up. And then, of course, you can go ahead and study interactions between these hemodynamic parameters and your experimental conditions. And without going into all the bulk of information that you get, I just picked out one example. So here you have a view of the right superior temporal gyrus. And you have two areas here depicted in white, which are essentially an overprojection with the primary auditory cortex that comes up early with respect to these green areas over here that you can see that come up, say, about 300, 800, or 1 second later than these areas in the auditory cortex. And interestingly to say is that these white areas over here are independent of the correctness manipulation, while these are dependent on the correctness manipulation. So you have these early areas where the sentence is just perceived, and you have these later areas where part of the sentence is understood, or the grammatical violation is detected. Important to say that in this experiment we were able to resolve temporal differences in the lag times down to about 250 milliseconds. And what was also very interesting to find is that the duration of the sentence presentation was proportional to the HR dispersion, so to the duration of a hemodynamic response, with a slope of 1.02 per second. So it's really almost proportional in this area. We are very much aware that this linearity is only given over a small range because our sentence presentation varied only between 2.4 and 4.2 seconds. But that's a realistic way of treating this. Another example, here we have a classical Sternberg paradigm. And you know, first I show a few items to a subject, and we have a certain delay phase, and after that phase I show another item, and the subject is asked to respond whether this item has been in the set before. So first we have the cue phase, then we have a delay phase, and then we have a probe phase. And using this hemodynamic modeling, I can distinguish which of the areas are active in all three phases, such as the green ones over here, which are active only in the cue and the probe phase, and which are active only in the cue phase, and which are only active in the response phase. Yeah? So I can distinguish the contribution of different areas to the different phases. In addition to that, I can also measure how long each area is active in each phase, and how much this depends on the stimulus conditions. So how much this depends on the number of items shown, or on the type of items shown. And this is all something that is possibly, but not in its completeness to get from standard statistics. Of course, this is a very simple approach, and we tried out a lot of different extensions to this simple method. First of all, you may want to have a measure whether this modeling really does something good. So you want to have some goodness of fit criteria, and you can develop some statistical criteria that simply tells you whether the modeling was successful or not. There are always some trials where the signal-to-noise ratio is higher, or where you have some artifacts and you do not want to carry values from a misadaptation over into your statistics. So this is almost automatical, and you can introduce some threshold where you say, okay, only values above that level I want to carry over into my statistics. Of course, the process of selecting the regions of interest can be made automatical. So you either can select, say, the n most highly activated regions, voxels around in a certain region. And you can also do this with respect to a subject group. So you can look at a spatial pattern of the activation and select a similar pattern of activations in the next subject over here. You can extend this model, of course, when you have more than one response during a given trial. And for instance, I showed you this in the Sternberg paradigm. because we have a stimulation during the cue phase where we present the different cues, and we have another stimulation during the response phase, so we can multiple events during a single trial. The analysis of parametric designs with rapid randomized stimulation is possible. I said in the beginning, if you remember, that it's best done on event-related experiments when you have an 8 to 14 second interstimulus interval. But you can also go down very much down to this, and Thomas has shown such an example where you essentially, from the overprojection of all these responses, you can essentially go down with a mathematical model to individual responses. But they are then meant per class. So typically you have in this experiment a few classes or a continuously varying parameter that you need in order to regress the individual responses out. You don't need to go with hand-driven or automatically drawn ROIs, but you can guess that from the data. So you can do a, say, per voxel-based modeling and introduce an automatic segmentation on the parameters that you get. So you can compute the parameter map voxel-wise and then aggregate voxels based on whatever criterion you have to segment those maps and generate those ROIs automatically. And finally, other people have transferred all of this into the Bayesian domain without the need of defining a specific hemodynamic model in the end. So this turns out automatically in the end from the analysis. Suffice to say that what we're interested in are the modeling parameters over here. I should mention a few caveats when you want to do this. First of all, we need an event-related experimental design best in a parametric form, just for the simple reason that you get the best results from this modeling when actually you model over all the trials that you have. So suppose we're taking in the Sternberg paradigm the number of items I show. Then the number of items is varied in a parametrical way over the whole experiment. When I'm now modeling those hemodynamic responses, I can do a regression over all the hemodynamic responses I have, because I'm interested essentially in the slope, in the change of my HR parameters with this experimental manipulation. And this is also where you, of course, get the highest time resolution, because you can now think of each trial as a data point, and the more data points you have, the better your time resolution will be. You should be aware that all these physiological parameters underlying the hemodynamic response are finite. So the slope of the hemodynamic response and also the downslope is rate limited. This is why the modeling parameters gait, lag, and dispersion are not independent of each other. If you have a higher response, that needs longer to develop. And a higher response will also take longer. So you need to take all these variables as confounds into your statistical context when you want to analyze them. Of course, you can come up with a more clever model, including some physiological variables, where you may sort of inverse this and infer about, say, the true neuronal stimulation length or something like this. But in the simple way of analyzing it, you need to have all the three variables as confounds in a model. You should be aware that system and physiologic noise may make it impossible to get a successful modeling in all trials. So you will have some missing data in there. And you need a certain amount of activation or a certain signal-to-noise ratio in order to do this modeling, but this is given with all scanners that we have today. Important to remember is that we are looking for relative effects. It does not make sense to compare absolute lag times between individuals because they are highly different. What we are looking for is a shift in the lag time with respect to experimental conditions in a specific individual. And we want to replicate this in another individual. So in the end, we're perhaps just interested in the sign, whether this area always comes up after that area, and whether this is the same thing in another subject. Instead of modeling saying something this is 8.3 seconds or so. So we're very much interested in relative effect, be it slopes or just signs of the activation. Of course, the choice of the modeling function is arbitrary, and there's been a lot of discussion in the literature which would be the best modeling function instead of Gaussians, gamma variates, wavelets, sinusoids, and so all of them are viable because it's an empirical model. We just use the Gaussian functions because the parameters are so easy to interpret. So you immediately get something like the time to maximum. This is something that you can understand. When you want to do this with a gamma function, you can of course compute the maximum for this, but this is an additional step. And another thing that in terms of numerical modeling, the Gaussian function behaves quite well in a nonlinear regression model, which is not true for gamma variates and some of the other methods that were used. So taking a look into the literature, it is not very well known, I would say, that you can model hemodynamic responses with that precision. But essentially the list is long, and you got publications from all major labs that more or less replicated this finding. The first one was actually Menon who published this. He found a high correlation between the stimulus presentation delay and an HR onset delay, and we published our paper 3 months after him. And there was a lot of people coming after that. So for instance, Hernandez is given a time resolution of about 200 milliseconds with a 95% confidence interval with a TR of 1 second, and you certainly can go down to this. And here's a review for you if you want to read more about this, what people have done in this area. Of course, there are other methods for estimating the lag of the hemodynamic response. You can use two gamma basis functions. The pro of that is that it matches the overall shape better. Of course, when we use a Gaussian function, we do not model the undershoot. We're not interested in the undershoot here, you could say. But if you have overlapping trials, this may be an issue for you. So there is a plus in the argumentation that this may be a better match for the function. But at least in this way, they are estimating the parameters over here. You need a spectral estimation, so you need the whole time series, and you do not get per trial information. And you do not have directly a duration measure. You can get that duration measure, of course, from the modeled response, but that is the second step over here. You can check the relative delay, the time between two time series in different regions using cross-correlation. That is very simple. It's basic signal processing, and you get relative timing measures between two brain regions. On the contrary, you don't have per stimulus results over here, and you have to assume that both regions do the same in all stimuli, which is not necessarily the case. You can use the phase spectrum. This is a very stable method and conceptually simple. And again, you get a relative measure between brain regions. Again, you don't get per stimulus information. Or you can use a multivariate autoregressive model, which is also conceptually simple and which you can use to analyze brain networks. And this is what is also contained in SPM, for instance. Again, you don't have per stimulus information available. You can go on then and use this in the framework to analyze brain networks. And we heard yesterday already a bit about the Granger causality. So you can come up with some measures, information theoretic measures about the coherence of two time series and the influence of two time series. And you can do it using this autoregression model, or you can use it, do it using Markovian chains, as we heard yesterday from Clark. In the very end, this means just that you can use this temporal information to learn about which area drives one, so you can give more meaning to the relative temporal order. And I understand that a lot of models have been developed here in recent years. So let me summarize. I wanted to give you some idea that the hemodynamic response carries more information than just the activation amount, than most of people really evaluate. The duration of the hemodynamic response and the time to maximum of the hemodynamic response allow additional inferences about neuronal processes. For instance, especially when you want to model the sequence of activations. Using today's method, I think a temporal ordering down to 100 milliseconds is possible in almost any experiment. And based on a TR of 1 second per, for instance. Thus, cognitive processes can be ordered. Of course, a lot of the cognitive processes that we are interested in are in a time range below 100 milliseconds, but in the end, this is just a thing that may be different with a higher time resolution or more trials, or of course you always can do ear-peer in addition to this. Due to the large intersubject variability, relative measures must be studied in individuals. And if I read most of the publications on this correctly, then they were studying groups of subjects, and they were just puzzled by the variability. If you go to an individual, the hemodynamic response is a really precise physiological sequence of actions. So you will get relatively constant measures. Of course, there's always a day-to-day variability, but once again, we're looking for relative measures, relative in one experiment. And we're perhaps only looking for the sign, whether this always comes later or always comes through. Once we've done this individual analysis, we can use any more clever strategy to pool this information or compute regression slopes for my whole experiment, and come up with more clever ideas than just the standard statistics I was showing here. Network models, you name it. But you should be aware that the parameters as analyzed here are not independent of each other, so you have to use them in confounds when you do some analysis over here. And in the end, of course, this relative information can be used to infer something about causality over here. One must be careful when thinking of this. For instance, some things that are very well known in ERP experiments is something that we find again over here. For instance, in the Sternberg paradigm, we see the supplementary motor area active during the Q phase, which does not necessarily make that much sense, because a response is not expected over here. A response is only expected over here. But we see this active, and this is also going through the literature. Very often the SMA is activated very, very early after stimulation onset. This is what correlates to the readiness potential. So it does not necessarily mean, because we think that this only has a role very late in the whole cognitive process, that it couldn't come up early in the whole section over here. So all these temporal information must be taken with care. Of course, if you want to read more, here are a few papers from our lab. There are a lot of other publications on this area. I just wanted to make you aware that there may be more than just taking a look at activation statistics. I thank you for your attention and be happy to take any questions.
We're officially open for discussion now. I'll leave it to Dr. Kruggel to handle any that are specific for him. If you have other general questions, let's go.
Yeah.
What do my collaborators have to do to get me 100 millisecond time resolution?
Well,
Listen carefully,
I was giving you a small idea what you want to do. Well, use an event-related experimental design. Use a relatively long ISI, so 8 to 14 seconds.
Big risk.
Yeah? Use a relatively short TR. Perhaps use just a few slices where you know that you have the activity you're interested in. We had some experiments with just 4 slices. We had a pre-experiment where we sort of nailed down the areas that we were interested in and just record those 4 slices. Yeah? And then do this analysis. Yeah?
So you just cut down the time for your whole brain scan to just a few areas, so you get that rapid.
The point is that you have measurements every second, but in modeling, you can get to a sub-second range.
So I guess you better tell me later, not one of the
Yeah.
collaborators about that.
I mean, you're sampling a long function,
Yes,
and you can get that function fairly accurately from a
Yes.
small number of samples. In fact, it's
Exactly.
possible to get it
exactly.
from just a couple of
Yeah.
samples, even though it,
Yeah. Imagine you would have a sinusoid that you subsample. Under certain assumptions, you can recover the frequency and the maximum.
the signal
Yeah.
to noise.
Yeah? The signal to noise is, of course, an issue. But as said, from my experience, we did most of these experiments, say, almost 10 years ago. So I think that the current scanner, everybody has 3 Tesla scanners right now. So, and if we have a, say, response in the order of 2 to 4%, like you were saying, that's pretty good. You can do that. You cannot do this with every region. You will not get an answer in every trial, but it works if you have, say, primary cortices, large activation areas, and secondary cortices. You can try it. Yeah? I mean, I cannot guarantee that it works for every experiment and every human being, but it's a method. You can just model it and see what you get out of it. It's a so simple manipulation. I mean, this, the basic modeling context is 10 lines of MATLAB. Yeah? So an experienced graduate student can send that up in a day. Yeah? So it's not a big issue of trying this. Yeah.
How identifiable are the parameters?
What do you mean by how identifiable?
Do they trade off against one another?
Yes, of course. This is what I said. You have to be aware that the slope of the hemodynamic response is of course rate limited. It doesn't go up like this. It's not possible. It's not biophysically plausible. So you have a certain interdependence of the parameters. This is something that you can simply study in theory by, say, making Monte Carlo simulations and look at the error plots you get for the parameter estimation. And of course, this is also something that you will see when you model your experimental results. So you need to have all the 3 variables as confounds in your experiment. So suppose you're looking for the duration. Your variable in question is the duration of your stimulation. Then you need to put the gain in there as well, because if you have a higher gain, you also have a longer duration. So that is a confound. Yeah?
So in these event-related experiments,
Yes.
people tend to overlap the trials to some extent.
Yeah.
And I was just wondering about the advantages of the higher order kernels that Tom was talking about, if there's any benefit in considering that versus the purely linear models that people usually use.
Of course. I mean, I only showed here the very, very simple version of this. And I was just trying to stick to this in order to sort of spread the message. Yeah? You can use any more clever methods to analyze the data. Like I said, other people were taking over this into a Bayesian context without having a predefined model underneath. So you can do any more complex ways over here. I must admit that I don't have experience with that. I left that topic sometime, but hemodynamic responses are still hemodynamic responses.
Just raising a discussion item here.
Yeah.
I'd like to get some guidance on this.
The problem is you have many more parameters to estimate, so once you move outside the sensor area, you're...
A little louder, Tom?
Yeah, the problem with any sort of more sophisticated thing like a Volterra analysis is that you have more parameters to estimate. And so once you move outside, say, motor and visual areas, your SNR takes quite a bit of a hit. And so it's probably not practical for a lot of studies to do it. But you could try it, but the problem is then you have to use basis functions to sort of reduce the number of estimates, but then you're imposing bias. And then if you're looking at these small features like slope and things, then you have to worry about how much bias you're introducing from your choice of basis functions.
By the way, some of the results you've shown, the paper by Schröter was generated also in our lab that was based on near-infrared spectroscopy. So that works also in near-infrared spectroscopy. Yeah.
Don, should we adjourn at this point?
Well, let's find out if people have any other comments or questions. And
I was hoping.
What about you? We'll start off with you. Why don't you go through the speakers and ask if they have any comments or questions
Tom?
of others that are here. I mean, you've got an opportunity to question somebody.
So I have a question for Tom, which is really like the implications for his results on, say, so you talked about disease, but presumably this also applies, say, to developmental.
A little louder so we can pick it
So
up.
longitudinal and developmental imaging, I mean, what would you say in terms of if you wanted to adopt that strategy and to look at sort of comparing different ages, developmental children versus adults at different ages, what sort of measures would you need to be able to cope with the problems you're identifying there?
Yeah, I would say that we don't really know the right answer yet, but probably the best strategy is to start collecting the additional data that you could use to inform the interpretation. So I would think that, we're advocating people at least acquire the baseline blood flow, because you need to. We know that baseline blood flow changes the Wolf response, amplitude and shape, and if you know you're going across populations with different baseline blood flows, it's at least another handle on the physiology. And I suppose if it becomes more easy to do, I mean, I think acquiring maybe resting state EEG might be just a simple resting state alpha power. Maybe that might be something to start thinking about. We don't typically recommend that simply because it's most people do FMRI, just do FMRI. But maybe we need to expand and think about easy things that you can add, short of a full EEG experiment. So I don't know. I think our thing has been there are simple things you can add. You could add a resting state run. You can add a baseline blood flow run. You might be we're looking at these venous oxygenation measures, things that maybe add 5, 10, 15 minutes to your scan, but give you very important sort of handles on the baseline physiology. So that would be my recommendation, and then we'll figure it out later.
Nicole?
I have a question about the global signal thing.
Sure.
So you're pro global signal regression for the resting state?
I don't think I would exactly be quoted as saying that.
Okay.
I do think it seems like the initial concerns raised by Murphy and others were too extreme in the sense that if you do these other ways of coming up with global signals that are not where Murphy was saying that if you do the whole global signal, then mathematically you're forced to have these negative correlations. But what we're finding is even if you do things that get around these mathematical sort of constraints, you still sort of see this effect. And so there probably, my current thinking is there probably are these anti-correlated networks. And because we actually see it when we don't, like there's a recent paper by Chang and Glover showing that if you just take out more of the physiological noise with more sophisticated methods, you start seeing these anti-correlated networks better. And we just did a study, which I showed it, but I couldn't explain it, which is if you look at the EEG, if you take the EEG data and correlate it with the bold data on a voxel by voxel basis, you can also pick up these anti-correlated networks. And so I think they're real. So I think Murphy and others was sort of maybe went too far in saying, they're not real.
Because I try to differentiate, like we know not to do it in task-based FMRI. But when I think about it, both situations seem the same. You have a regressor that is highly correlated with most of the brain.
Right.
And and if you model that signal out, you're gonna get negative activation. So in a way, they're the same,
Yeah.
so I'm just trying to find things to differentiate.
Right, so that's the tricky part, because even if you do it so it's mathematically correct, or you're not double dipping, you're still, you have these things that are correlated, right?
Right.
And so the question is, what are you, I guess the question is, what is, so the Fox sort of, the Rakel group is arguing that what you're actually looking for is, there's this sort of fluctuation, and I think as time goes on, we're going to figure out more and more of the physiology of that fluctuation. And but short of that, if there is just this weird fluctuation that we don't understand, what we want to see is differences with respect to that compound. So I'm not sure that I would say the global signal, you should use it, but I think the evidence is saying that it's, maybe, it's not a bad thing to do. It's not, as long as you do it right, it's not a bad thing to do, but then interpretation is still up.
Russ, you've been very quiet hiding there in the back.
No, I guess they used up all my question energy yesterday. I think that how to deal with this HRF modeling stuff, I think is a really interesting question, because everybody again is kind of settled on one approach of using this SPM HRF, and I think some of your work suggests that you might want to think about other ways of trying to do that. There's such a huge, it's like any of us could spend the rest of our lives kind of plumbing one little part of the analysis space, and there's kind of an explore-exploit dilemma for us when we're doing science, right? Because we don't want to spend all of our life sort of trying out different sorts of things. So it's hard to know, how, what, scientifically, what is this going to, what is this kind of approach going to do for us, as opposed to just taking the canonical HRF and doing something with it. And I don't know that I have a good handle on that.
For instance, you can get an idea how long a region is involved in a specific task.
But again, what scientifically, if I care about understanding how cognitive functions are implemented in the brain, how does that answer help me answer the question that I'm interested in, right?
Think of the memory experiment. There may be some parts in the brain that would take as long part as your stimulation was, and other parts may just take part much shorter than that. Yeah? So this may help you in understanding the way a region contributes to the processing. Yeah? I just wanted to say that it's not only the activation amount, but it's also the duration. And if you look at ERP people, they're only talking about time. Yeah?
Sorry, the duration and the amplitude are correlated, right? So
to a certain point, they are not completely independent.
I guess if you put them both in the model, then you'll get separate contributions.
Yes.
Well, I had a frivolous question not entirely frivolous question for Tom, but I'd rather wait till the people are done with the serious ones.
That's too intriguing.
Does anybody have a serious question?
Duncan, you have a question or a comment?
Yes.
Not really.
Well, really a question you raised is what led to this conference. So, are you satisfied now or not with the answers?
Sorry. I mean, that's an impossible
I know.
question. My problem is that my level of interest is at the level of behavior. And I'm not sure I'm getting all that informed about it from these kinds of data. I noticed that early on somebody said that we needed to have a better, I guess it would be a taxonomy of psychological phenomena that need to be explained in terms of neurophysiology. And I'm personally just working at that level of behavioral taxonomy. And I'm not at all convinced I've heard anything at this level that is very informative to me of what is going on at Haver. I think the connections are just not there yet. I mean, I won't.
I guess I would disagree with that in the sense that I think, this group hasn't focused on those connections. I and others have written trying to make the argument that you can actually use imaging data to test models that are framed at a psychological level. And I think that there are at least a few examples where that can be done. You can believe them or not, but at least you can make an argument.
Presumably, for behavioral models that postulate some internal structure, there might be a possibility of a connection. Like,
Right.
those internal structures that people have postulated in the last 60 years that I've been aware of. It's not clear what level they're at vis-a-vis what the physiology. I mean, it's real guesswork. There are other kinds of models, kinds that I work on, that are entirely at the behavioral level. No postulated internal structure. They're looking at properties at the behavioral level, deriving predictions from those properties. And their connection to these kinds of data seem very tenuous.
I would agree with that, sure.
To be able to distinguish between psychological models with neural data seems to me to require that the psychological models have some neural postulates, and it's been my experience that the descriptive, the behavioral model can always, the premises and postulates of the behavioral model can always be separated from their neural postulates. I remember some years ago there was a lot of excitement about backward masking, and there were 3 alternative mathematical models that described them, and 3 postulates. Each of the systems had their own neurophysiological postulates. Well, the mathematical situation changed completely when it was realized that all 3 of the mathematical models were essentially duals of each other, so they weren't different. But the physiological aspects were different, but there was no way to test them. And
So-
unless a model has the physiological postulates or even cognitive structure of some kind, as Duncan said, it seems to me there's no way that you can distinguish between 2 ordinary behavioral models.
Right, you can distinguish between behavioral models, sure. You can distinguish between cognitive models to the degree they make claims about representations, just as Duncan said. If the models make claims about, the representations that sit between, input and output, then, you can usually come up with experiments that can use imaging to try to give you, obviously they're not gonna, kill or, completely, they're one bit of evidence, right, in favor or against a particular theory. And you can ignore them or not, but you ignore them at your peril because they're useful information about the nature of those intermediate representations. If you don't care about, if all you care about is mathematical theories that describe the nature of behavior, right, and you don't care about describing what goes on inside the black box, then imaging isn't going to do anything for you, sure. But if you care about what's going on inside the black box cognitively, my argument is that imaging can actually help you distinguish between theories sometimes.
If some of the internal structures are hypothetical constructs that don't really have a lot of substance themselves, then you might go looking for intuitions or phantoms of one sort that will never show up in a FMRI signal.
Sure, yeah,
Well, that'd be
there's a
great
lot of ways you
evidence,
could fail.
wouldn't it, if they never showed up?
Pardon me?
Wouldn't that be great evidence if they never showed up?
No, because the complexity of the system is such that you always are going to have the possibility of subtle
Yeah, the
encoding.
unicorns could all be hiding
Oh.
somewhere, yeah.
Or they're all in this.
Perhaps I wanted to add something.
Mhm.
In terms of the brain networks, something that I think was hardly discussed over here, you also have the possibility to change something to the physiological model we're talking about, either by examining patients with specific lesions, for instance, and see how much is different in those patients, or introduce sort of artificial lesions by combining FMRI with magnetic stimulation in order to suppress the activity of certain regions. So you have other possibilities of interacting with the process in addition to the experimental manipulation. But again, this means that you have a construct in terms of a network and not in terms of a mathematical sometimes they match.
Picking up on that point that you made, it's a sort of an interesting statement to say that if we only care about an input-output function and not what happens inside the black box, FMRI is not going to be of any help. If that were really true, then it would follow that FMRI is only good for uncovering some mechanisms of neural work, or how some substrates of this black box work together. But they would not then be informative. At no point would they inform an input-output function. And that I find very, very troubling, because it says that nothing I could learn about the brain could give me a predictive theory of what an input to output would be.
No, that's
not what it says.
That's not what it
Absolutely
says.
the opposite.
Right. My claim was that, Duncan doesn't, nothing that is going to be said with imaging is going to affect the theories that he is building about input-output relations. That doesn't mean that you couldn't use, Francisco and I and others have shown how you can use imaging data to actually predict very well, given some input, what is the output going to be.
Precisely. I wasn't claiming that otherwise, but it seemed to me that there was a hidden implication in your point. But therefore, it would seem that one of the burdens of those that are doing FMRI would be to show that understanding some internal mechanism in fact give you novel predictions. And I say novel because if they're not novel, they're not that much worth, having all this technology. You can do it with pen and paper. Some novel predictions about these behavioral, some behavior of any kind.
Sure, to the degree that the way that you test cognitive models is through behavior, then yes, I agree that that's true. Imaging can give us information about cognitive models, those make predictions about behavior. So yes, that should be the case. I think you're right that should be the end goal. I don't know of any good examples where, I certainly know of examples where imaging data can help adjudicate between models that are indistinguishable on the basis of behavior, right? And that's, almost all cognitive models in the end become indistinguishable on the basis of behavior, at least when they get complex enough, right? And that's actually a place where I think imaging can be really useful. In category learning, where I've done some work, you have these, single system models and dual system models, and anybody who has one can tweak it to make it, sort of adapt to any of the data of the other. Imaging provides a really good way to test claims about, single versus dual processes, and I think that's a place where imaging has been really useful in sort of arguing in favor of one class of models and against another that were not distinguishable on the basis of behavior.
One thing, if the discussion is drawing to a close now, is that I'd like to speak for all of us who have been here today and say thank you to Don and Duncan for their invitation and their hospitality, and it's really been an experience, and for me, and I'm sure for many of us, a learning experience. That's the name of the game. Thank you very much.
The appropriate people to thank are not me, but it's Don and Hal Stern, who unfortunately has not been able to attend very much.
Can I add to that list? I bet Janet Phelps
Janet
contributed.
Phelps has done a lot.